Okay, let's just jump right into it. We all learn this in school, right? Gravity pulls on stuff that has mass. But then you hear that light, which is famously massless, gets bent by gravity. How does that even work? It feels like it breaks the most basic rule of physics. But the answer, well, the answer is just one of the most beautiful and elegant ideas in all of science.
So, yeah, that's the central mystery, right? Gravity's whole deal is attracting mass. Light has zero mass, so this just shouldn't be happening. And yet, we see it. We have pictures of stars bending the light from other stars far behind them. For the longest time, this was a massive headache for physicists. And the first person to really start cracking this puzzle probably isn't who you think it is. To start figuring this out, we actually have to go way back, all the way back to the guy who literally wrote the book on gravity, Sir Isaac Newton. Now, I know what you're thinking. Newton's physics is all about mass, so how could he possibly have an answer? But believe it or not, hidden inside his own work is the key to a seriously mind-blowing explanation.
It all starts with a really simple thought experiment we can all picture. Imagine you're holding a basketball in one hand and a feather in the other. You drop them, what happens? Easy, right? The basketball just thuds to the ground while the feather kind of floats its way down.
But, and this is the important part, Newton says, okay, what if we could get rid of all the air? Let's imagine doing that same experiment but in a perfect vacuum with zero air resistance. Suddenly, something pretty amazing happens.
They hit the ground at the exact same time. And this isn't just some theoretical idea. People have actually done this. They've built these huge vacuum chambers on Earth to test it. And maybe the most famous example was an Apollo astronaut on the moon. He dropped a hammer and a feather. And yep, they hit the lunar surface together. It's wild to see.
So, what does this actually tell us? It reveals something super fundamental about gravity. Here on Earth, everything accelerates downwards at the exact same rate, 9.8 meters per second squared. The big takeaway here is that an object's mass, it just doesn't matter. It has absolutely nothing to do with it.
Okay, and this is where Newton makes his brilliant logical leap. He's thinking, all right, if the acceleration is the same for a basketball and a feather and a tiny speck of dust, if mass is totally irrelevant, then why stop there? Logically, shouldn't this rule also apply to something with zero mass, like, say, a beam of light?
Now, I bet your brain is screaming, hold on a second, because F equals mg, right? Force equals mass times gravity. If light's mass is zero, then the force has to be zero. And if there's no force, there can't be any acceleration. That's a totally logical objection. But it turns out there's a really interesting mathematical quirk hiding here.
Yeah, the math is a little bit of a brain bender. See, to get acceleration, you divide force by mass. For light, that's 0 divided by 0. And in math, 0 divided by 0 isn't 0. It's what's called an indeterminate form. It basically means your equation blew up and you asked the wrong question. The real trick is to see that the mass variable, the m, is on both sides of the full equation, so it just cancels itself out right from the start. Once you do that, you're left with a constant acceleration. The mass was a distraction the whole time.
So, okay, Newton's logic gives us a pretty clever way to argue that light should be affected by gravity. But this whole mathematical trick, it's actually pointing to a much, much deeper mystery, one that was hiding in plain sight in Newton's own formulas for hundreds of years.
It turns out the word mass in physics is kind of doing double duty. It actually means two totally different things. On one hand, you've got gravitational mass. Think of this like your gravitational charge. It's what determines how hard gravity pulls on you. Then, on the other hand, you've got inertial mass. This is all about your inertia, how much you resist being pushed or accelerated. And this distinction, this is where the real mystery kicks in.
So here's the big secret, the big question. Why on earth are these two completely different properties, how much gravity pulls on you and how much you resist being moved, why are they always exactly the same? I mean, think about it. There's no law that says they have to be. It's like finding out your shoe size is always exactly the same as your age in months. It's weird.
And what's really wild is that Newton himself had no idea. He just shrugged and was basically like, I don't know, it just is. For him, and for every physicist for the next 2 centuries, it was just chalked up to a bizarre coincidence of the universe. It just works.
And this is our cue for Albert Einstein to walk onto the stage. Einstein had this core belief that the universe doesn't do coincidences. There had to be a deeper reason why these two types of mass were identical. And his obsession with this coincidence led him to one of the greatest insights in human history.
He came up with another thought experiment, one he called his happiest thought. He asks you to imagine you're standing in an elevator with no windows. Suddenly, the cable snaps. You are now in total freefall. What do you feel?
Well, you'd feel nothing. You'd be completely weightless. If you took your phone out of your pocket and let it go, it would just float right there in front of you. See, your phone, the elevator, everything is falling at the exact same rate. So from your point of view, inside that box, it would feel exactly like you're floating in deep space, miles away from any planet.
And this leads to Einstein's massive breakthrough, the equivalence principle. He realized that if you're stuck in a closed box, there's no experiment you can do to tell the difference between being in a gravitational field and just accelerating. So he asked a crazy, brilliant question. What if they're not just indistinguishable? What if they are literally the same thing? What if gravity isn't a force pulling us down at all?
And that one simple shift in perspective changes absolutely everything. You see, Newton looked at someone standing on Earth and said, "You're stationary, and a force called gravity is pulling you down." Einstein comes along and says, "Nope, there is no downward force. You're not stationary. The ground is constantly accelerating upwards and pushing on the bottom of your feet. That feeling of weight you have, that's just the floor pushing you up." And just like that, the whole mass mystery is solved. Of course, gravitational mass and inertial mass are the same, because what we've been calling gravity is just the feeling of our own inertia resisting that upward acceleration.
So with this completely radical new idea, that gravity is basically an illusion caused by acceleration, Einstein can finally go all the way back to our original question about light. And he can solve it not with some mathematical trick, but with a really beautiful and surprisingly simple explanation.
Let's go back to that elevator one last time. But instead of falling, this time it's in deep space, accelerating upwards at 9.8 meters per second squared, the same as us on Earth. Now imagine someone inside shines a flashlight from one wall to the other. That little particle of light, the photon, shoots out and travels in a perfectly straight line. But here's the key. While that photon is flying across the elevator, the floor keeps accelerating up.
Okay, so what does the person inside the elevator see? Remember, from their perspective, they're not moving. They feel stationary. What they see is the beam of light leave the flashlight at, say, eye level and then hit the opposite wall way down by their feet. To them, it looks for all the world like the light's path curved downwards.
And that's it. That's the answer. Gravity doesn't bend light. It never did. Light always travels in a straight line. The bend we see is just an illusion. It's not the light that's curving down. It's us, on the surface of the Earth, who are on an accelerating path upwards through spacetime. The ground is literally rising up to meet the light beam. The whole mystery was never about force or mass. It was about perspective and geometry.
This one elegant idea explains everything, from why a feather and a hammer fall together to why starlight seems to bend. But, like all great answers in science, it just opens up even bigger, weirder questions. I mean, if we're all constantly accelerating upwards, does that mean the Earth is actually getting bigger? And how does all of this connect to the idea of curved spacetime? Well, that's a story for another time.